So we just saw two different hypothesis sets, and then we saw two different data sets, and their behavior varied depending on what kind of hypothesis set we were using. And so definitely there is a relationship between multiple or like different data sets depending on their distribution and the hypotheses that we select, the prediction that we finally have on this unknown new test point, right? So what we're going to look at is the expected behavior with data sets. Now, the entire analysis, like the entire theory, actually relies on first generating a data set, getting a hypothesis, a final hypothesis, and then eventually predicting something on that, right? So let us begin with that process. So basically, we can have like different multiple data sets given a hypothesis, right? Given a hypothesis set, and we can have like different predictions on that, right? So let us denote each of the data sets that we have with D1, D2, D3, and so on up to DM. And let us assume that for each of these like Ds, we have a final G that we get, right? Depending on whatever hypothesis set we are using. And then the way we are labeling this is G of D1 because we used data set D1 to get this G, and this G of D2, G of D3, G of DM, right? Now, once we have this G, right, we need to evaluate on a test point, which is a fixed point, just like we did in the previous example, like we were trying to predict the value for a given test point, right? So the way to the way we are like denoting it in this derivation is by saying G D of 1 on X, right? Because it's just a function. So G D 2 of X, and similarly here, I'll just like continue G D M of X. So what exactly are we interested in? We are interested in the average prediction over all data sets. Like what is the average prediction of X on all over, like all the possible data set generation that we did, right? So the average G bar of X is going to be nothing but the arithmetic average of I is from 1 to M and G di for X. Okay, so now if we have like a huge number of data sets, what this value approaches to is the expected value of this average, right? So for maybe large data sets or larger data sets, this value will approach, and that's why I'm using for approach an arrow, to the expectation over all these data sets D, this average essentially. And now I'm denoting it over all data sets as G of D for this new point X. So basically this D is representing randomly generated data set, any of these data set that was randomly generated, and this entire thing is my expected prediction, right? So by definition, this is going to be my expected prediction. Okay, great. So this is my expected prediction. And just like this expected prediction, I can also have the variance of my prediction, because obviously for each of these, as you can see, my prediction is varying depending on a lot of factors. And so I have to take the expectation of that variance into account. So by definition, and again, this is from some basic probability statistics class, the variance of my X, the variance of my prediction is going to be 1 over M, I equals 1 up to M, my G di X for any of the like 1, and how much it like deviates from my average prediction, right? That's the definition of variance. So that's that, and the square of that. Now, as again, data sets become large, this entire thing will approach to the expectation of that randomly generated data set, and G D of X minus G bar. So this is like generalizing this entire thing, right? G bar of X whole squared. The expectation of this. So this is my variance of prediction. This is the variance of my prediction. And this is the expected prediction. This is my expected prediction. Okay, Now, if you remember, we defined my out of sample error. Essentially, let's quickly jump to what I mean by out of sample error. This variability here is representing the error, right? So the error term was like f of x minus whatever g, for example, in this case was 0x and whole squared, right? This is essentially representing E out. This is my out of sample error, because if you remember the definition of E out, it's really telling me how much like I'm able to reach to the outside, like the universe of the entire data. And that's what I'm using this X for, right? To kind of represent how much I'm able to reach outside my training data. So that's what we're talking about. So the out of sample error is going to be written in general, something like this: f of x minus g di of x whole squared, right? Because square of error. Now for each of these like data sets essentially. So the average error is going to be, and let me just like add, or maybe I could have done here, but let me write the average. So this implies average error is going to be just like the 1 of m, the number of data sets. I is from 1 up to m, and then this term, f of x minus g di of x whole squared. Now, if you notice here, this is a constant, right? Although there is this like unknown target function that exists, but for us it's constant, and for like any problem it's constant. It is what it is, right? And if you think about this one, because we can randomly generate data, right? And so this is like a random variable, right? This for any data set D1, D2, DM, this is a random variable. So there is this known result from probability theory. Result from probability, most likely if you've taken Fox, you would know this, or any other like probability or statistics class, that this particular term can be divided, or like if you expand this essentially, because there is a constant and a random variable, if you expand this, you can write this term something in like this. So basically it becomes f of x, which is my constant, minus the average of the random variable, which we already calculated, right? So it becomes this plus the variance of x. And if I remember correctly, this entire, like there are multiple steps here, and mostly algebraic and like manipulation. It's also given in the textbook. So you can go and check the exact not like steps, but it's nothing but algebra, so I'm not jumping into that. Eventually we come down to this, like f of x minus g bar x squared plus the variance of x. Now here, this term specifically is the bias, like how, if you remember the picture that we saw, how far apart is my final g. So this is like the average predicted value, right, is from the actual f of x. This is my bias, and this of course is my variance, right? So the penalty I'll pay depending on the entire data set, and in a finite data set, whether I'm able to come as close to f of x as possible, right? So this equation here is known as the bias variance decomposition. And the bias variance decomposition of out of sample error is essentially based on square error measures, right? So that's how we derive this. And so finally, we can come up with this theorem. Let me write it down here. Let's see what the theorem states. So the theorem states that the expectation over any data set D of this value, this error term that we just saw, f of x minus g d of x whole squared, right, is equal to, maybe let me write it here only, f of x minus g bar. Now this is different from this, right? G bar of x whole squared plus the variance on x, right? Or in other words, this is equal to the bias on x plus the variance. Okay, and what exactly is this what is the theorem telling us? This is the expected out of sample error over data sets, right? So this is the expected E out. Okay, so the expected value over the test point X is like, you can further take the expectation on the left-hand side. So if we take that, then that would be the expected out of sample error with respect to all data sets and all test points, right? So we can further define this, that the expectation of X for this ED, which is already known, Fx minus GD X, yep, whole squared, and one more, right? Because expectation over expectation is going to be the expected value of the bias of X plus the expected value of the variance of X. Right, again, because we take expectation on both sides. So essentially we are defining the expected E out with respect to data sets and with respect to data sets and with respect to test points. So what does this equation tell us? What does this like entire sort of derivation tells us? It tells us that the out of sample error comprises of two parts, right? So this is my out of sample error if you think about it, and it has two important components. The very first one is my bias and the second one is my variance. So the first one is telling me how close is your average learned hypothesis is to the target function, right? Which is, where is it gone? Here, right? How close am I to the target function? And the second one is the variance, right? So this is essentially telling me in other words that you can do very well, but you cannot get there very often. You cannot get there very often because if you do, then you pay the price for the variability that comes into picture. Okay, so how does this entire analysis fits into our line example, the one that we did earlier when we were trying, like having two different hypothesis sets for two different lines? If you remember, we had h of x equals b, and let me call it 1, and let me call it 2, or maybe I called it 0 and 1. So let's call them that. Right, so remember these two hypothesis sets. In this case, what was going on? We saw that the hypothesis wasn't like changing a lot. It didn't change a lot. If we go back and see, the line was here in this data set, and in this case again the line was somewhat like in a similar position. But in this case, the line had a different slope and a completely different sort of alignment, I would say, or position rather. In this case, it has like rotated actually. It is in a complete different slope and different intercept. So what is going on in both of them? What actually was going on in the first one is that the bias was large, but there is no variance, right? There was a bias was there higher, but there was like almost variance was 0, I would say, right? Because it didn't vary that much. I still got to where I was, right? In this one, if you like, we were able to do well, right, with the right data set, I would say. But if we had a different data set, right, we did really bad. So in this one, my bias was small, right, but my variance was huge, right? And how does that fit into my approximation versus generalization? Bias is nothing but my approximation, the approximation part, and variance is nothing but my generalization part. And this is how my bias variance analysis and my VC analysis kind of come together. So I think I'll end this video here. In the next video, we'll see more which hypothesis was better under what conditions, and then stop there.